Yeah, so lintels for masonry walls. This is something that it's almost like a contentious topic. I've talked about this a few times, just few slides here and there over the last 7 years since we started Forest Consulting, we started working with IMI pretty much right away. And one of the things that I like to talk to people about when I was at the software company is how to do masonry lintels within finite element analysis software. And it caused a little bit of heartburn. And so through the last 7 years, again, we've really talked quite a bit about it. I just want to give you guys a little bit of the insight of why you can do things so much more efficiently with a masonry lintel than with, say, some other types of materials. And then there's other inherent benefits with using the same material from an aesthetic perspective, from a durability of the wall perspective, and we're going to try to touch on that along the way. This is a topic that, in all honesty, we presented 4 hours on masonry lintels. It was the 2 hours of kind of really heavy, like engineering and analysis of finite element analysis. I'm not going to do that to you guys today. I don't want to make you nervous, but I really had to condense this down into an hour. So I really struggled with it because I think there's so many different ways to look at why masonry lintels make so much more sense than steel lintels or precast lintels. Why you can really leverage your design of masonry so much more with masonry. So that's really what this talk is about. It's really trying to help you guys navigate towards why these make sense, why they can give you so much more capacity, why you can think about even thinning down your walls sometimes, using less grout reinforcing around your openings. There's just so much that you can do when you consider masonry lintels. We're going to talk about why people have been using other materials, but like I said, so there's a lot in here. There's some slides where, for the engineers, I spend a lot of time on here. I'm going to kind of just peruse through them. You guys can certainly have these handouts. For architects, if you guys wanted to pass these on to maybe engineers in your office, engineers that you work with, maybe just to start the conversation of why masonry makes sense. I don't think there's anybody in the room that wouldn't prefer to use masonry for the lintels because they're just going to give you a much better architectural design, a much better structural design. So I'd like you guys to start the conversation. So just 1 hour is not 4, and just 1 hour is not going to convince you maybe today, but like I said, hopefully starts a conversation.
You like that picture? Is that all right?
That's all right.
Okay.
Yeah,
okay. All right. Sam, he's been a structural engineer, and it's not that he's biased towards masonry. He designs all kinds of steel, concrete, post-tension, pre-tension. I suspect you've got involved with it. Masonry. So his background, he started up this firm in 2010. And the acronym stands for structural engineers. So he supports different structural engineers, but we partnered with them, the Illinois Structural Masonry Coalition, to assist on masonry because he had a skill set in masonry specialization, plus his background, he worked for 5 years with Bentley RAM software. So the evolution going to individual component design of masonry, now utilizing finite element analysis, is allowing us to more efficiently and effectively design with masonry, utilize masonry, maximize its capacity. So with that, that's what prompted us to have Sam present today. So with that, oh, look at that. Perfect. Good teamwork.
All right, thank you. A little bit about me. We talked about that already. We do a lot of different topics for the Structural Masonry Coalitions. We really try to hit all kinds of different areas. A lot of these kind of blend together. Lintels for masonry walls is kind of towards the bottom. It's what I would consider almost a little bit more of an advanced topic, engineering-wise, because we need to have some other basics and fundamentals, which again, you guys are going to get a slide or two on, and we're going to just kind of keep moving through. But again, planting seeds, really trying to get you guys to think about these things a little bit differently. So masonry lintels, we're going to talk about some of the basics. What are the options that we have for lintels and masonry walls? It's not just steel. We do have a lot of different options and a lot of different variations within those options. High performance masonry lintels, why that makes the wall better, the lintel design better. It really does make a lot of things better. And I think there's probably only one reason, and we'll talk about it, why you would ever switch away from masonry lintels. And we're going to talk about how we've solved that problem in the last couple of years. And we're seeing a lot of contractors solving it day to day So high-performance masonry lintels, and then using finite element analysis software. I'm not going to get into finite element analysis software or what exactly it is. It's tools that engineers use all day, every day in steel and concrete design. And so when I was at Bentley, we started teaching people how to use finite element analysis software for masonry. There's a lot of heartburn. I'm like, no, you guys, it's the same tool. This is the same thing that we're using all day, every day for steel, which is pretty easy to get around, but concrete. So concrete and masonry, they act the same. There's a lot of the same things and concerns that you would have for masonry design, you should have already had for concrete design, hopefully solving some of those problems. So using finite element analysis software, like I said, I'm going to give you some highlights today and just why using it really makes a big difference for masonry lintels. All right, so if I had 4 points that I really wanted you guys to remember, 4 points. Use the right strength. F prime L of 2500. Hopefully you guys have heard me say that before. Maybe not. If not, write that one down. That's we need to get into using higher strength masonry because it's very readily available across the country. 2500 is what I would call a standard value across the country. It's not something that's 60% lower than that, which most people use. Consider prefabrication. Number 2, that's one that, again, we have some contractors in the Midwest that all of their lintels in masonry walls are prefabricated masonry lintels. Like I said, though, I think the only reason to switch away from masonry is because of shoring. But if we're prefabricating, we don't have to prefabricate the whole wall, but just the lintel. We can solve the shoring problem, and then you can efficiently use your prefabrication to keep the erection going smoothly and easily. So I think there's some really good things that I can maybe share with you. Contractors are having different ways to solve this and how they're doing prefabrication, but again, we'll touch on that more. Moving control joints away from openings. I talked about movement joints in masonry walls, so this is just, again, a revisiting of that. Control joints at the edge of openings are what we do in veneers. And so don't get me wrong, I'm not talking about moving those joints away in veneer. I'm talking about the backup wall, the structural wall, or if it's a single white wall, that control joint does not belong at the opening. It should always be away from the opening. And when we do that, then our lintels can be designed much, much more efficiently. In fact, our overall wall design is much more efficient. But like I said, I'm not going to have a lot of time to get into a lot of the details of that, but I'm going to talk about why that's important for lintel design. And then lastly, masonry lintels, most effective, efficient, robust solution. It really gives us a really nice design. So those 4 points, if you guys remember nothing but those 4 points, I'll be very happy with today. And I think sometimes, the first few slides here, I think sometimes we overthink things. There's a lot of stone or masonry type materials that have been spanning over openings for a long time. And I think sometimes as engineers, we think that we need steel, we think that we need to do something else, but we've had some pretty old arches, lintels that have been around for a long time, right? I mean, these things are spanning over these openings, granted different loading scenarios. But even the Aztecs, these guys got these stacked arch openings. And some of these principles I think are good to remember even today, because if we can arch over an opening, if we can get these stacks to work and think about how that would span over an opening with no reinforcement in it, we can really easily see how we don't have to keep throwing steel at these masonry walls. As Jeff said, it's not that I don't like steel. We design steel all the time at Forest Consulting for a lot of engineers, but it doesn't belong in a masonry wall. We'll talk about that more. But again, use some of the principles that some of these older cultures certainly knew and recognized. And then at the Alamo, I couldn't help myself. I was standing under this unreinforced masonry stone arch, so I thought that was pretty cool, right? I mean, these things work just fine. So lintels are areas above openings. How does it define it within TMS? It's a beam. It's a member primarily resisting flexural and shear forces induced by perpendicular loads to its longitudinal axis. It's something that spans over a void, an opening within the wall itself. The different steps for masonry lintel design. Define the materials, geometry of the walls and openings. Certainly that's the most fundamental. Loads on the lintel. This is one where, again, we can go in 2 different directions with different types of materials. We maybe have different types of loads on our lintel. with different control joint locations, we maybe have different loads on our lintel. So all of this stuff working together is really important. So loads on the lintel, it changes as your different design options, as you go through the different design options, you can actually have different loads. It's not like a simply supported beam member that's going to be the same moment and shear no matter what we do. No, as we change things with the first, the geometry or control joints, my actual loads actually change quite a bit. All right, so getting into defining the materials, geometry of walls, opening size. First of all, strength of masonry. Again, we're going to just recap that really quickly. It's really important. I mean, for lintel design, depth of that lintel, amount of reinforcement at lintel, using the right strength is certainly very important. How the finite element analysis, I talk about this all the time. You can't be conservative by using low strength values within this finite element analysis. You have to be accurate. And so it's not conservative to just use 1500, to just use this low values. Be accurate with your modeling. So we'll talk about that. Geometry of the wall, geometry of the opening, height above the opening, all those different parameters are important to understand before we can actually do lintel design. We have to know all of those. And then last but not least, control joint locations. So what I showed up here first is the typical, right? And then we'll get into where I think it should be instead of that typical. Masonry as a system, masonry lintels still have these same reinforcement, grout, block, mortar, different properties within the different types of elements that make up the masonry system, right? It's not a CMU lintel. No such thing as a CMU lintel. There's masonry lintels. Within masonry lintels, we certainly have to understand the properties of the different materials that make up our lintels. Lintel block shapes. Sometimes these can be important for us as designers to know what different types of block shapes they're using out there. Certainly when you get to the job site, you don't want to expect something and then see something different and then throw up red flags and ask for more information. And so I just wanted to show you that these are certainly the typical lintel block shapes that everybody's used to, right? But just the typical standard stretcher block is part of a lintel, right? When we have a multi-course lintel, these are going to be the blocks that are going to be used at those maybe intermediate courses. We get to the top, it's probably also not a U-shaped block. It's going to be one of these flow-through bond beams, those knockout bond beam blocks where you can maybe reinforce the top of the lintel pretty easily with those blocks. So when you get into reinforced masonry lintels, we do have different block shapes that we should be expecting to see on job sites. It's not just those U blocks, all right? All right, so F'(M), again, I'm not going to spend a lot of time on this, but it should be 2,500. A lot of people are still using 1,500 PSI, and it kind of breaks my heart a little bit. I've been talking about this a lot, you guys, and I really want people to start navigating away from this. It'd be like people designing concrete to 2,000 PSI or steel to, well, whatever. But it should be higher. We just need to know where your block's coming from, know what mortar you're specifying, right? It's pretty easy. You know what block strength you have, you know what mortar you're specified, and we can establish the appropriate F'(M). It is higher. It's higher than 1,500. And so, again, I keep filling up this database more and more. We get to more states. You can see the Midwest fairly covered pretty well there. Get into the Dakotas. Anybody live in the Dakotas? I don't know. But we're trying to get this database more and more established so that people have more confidence in designing to higher strengths. If there was one value I wanted you guys to notice here, it's the one in the middle, the 4294, right? That's the average block strength out there across all of those different states, right? That's going to net us a very high design value, F'(M). That's the average. Again, that's not something that you would just use. You do want to go into each individual state, understand what the block there is available. But that's going to give us a design north of 2,500 PSI, right? So again, the website is forsei.com/CMU data. It's free to open, free to use. Get to know where your projects are. Get to know this information so that we can confidently say, no, F'(M) should be 2,500. F'(M) should be 2,800. F'(M) should be 3,000. Those design strengths make a big difference in all different types of aspects of design, but certainly for masonry lintels. We have to know what the strength is so that we don't have all 4-course lintels or 6-course lintels. When I'm talking about masonry lintels, I'm talking about 8 inches, 16 inches deep. They don't have to be very, very deep lintels when we use the right F prime M. All right. So last little bits here, and then just a little update, because maybe the last time I talked about this, maybe I was talking about the 2011. Within the 2013 MSJC or 2016 TMS codes, the new masonry codes, you can actually see these design strengths, block strengths that you need to get the higher F prime M, relaxing a little bit. The one in the middle, the one that I'm saying is a kind of a standard, things that we can use across the country, 3250, right? That's a lot lower than that 4294 that I just showed you guys, right? Just a couple slides ago I said, remember that number? That's a lot lower. 3250 is what we need for block strength to design to 2500 PSI. I'm not talking about stretching very far here, you guys. Makes a big difference. All right, so we know what the strength is. We know we're going to use a higher strength for masonry design all over the place, and we're going to know that when we get into lintel design, we're going to be more confident that we're going to be using higher strength elements. All right, so getting into the geometry of the wall, control joint locations. Get those control joints away from the openings. This is not what should be standard. We should not have joints at openings for reinforced structural masonry walls, right? For an unreinforced wall, for a veneer, just fine, but we're not talking about those right now. For a reinforced wall, we need to move those joints away. They should be sliding over, some distance away. I try to give people some recommendations here. Control joints are not needed at the edge of the opening because there's reinforcement all the way around the opening. Smaller openings, we could probably have the control joint even 8 inches away, just one course away or one cell away would make a difference in the design. If it gets to be a larger opening, maybe 2 feet away is probably where we want the control joints located most often, in that structural reinforced masonry wall. And you get into unreinforced walls, that's when you put the control joints at the openings. And then, again, other things that we need to know about the overall wall, we need to know the height above the opening, right? That's going to make huge factors in determining what the actual force is within the lintels, and I'll show you how that works in a second. But last things about control joints, again, these are conversations that I don't like to have. Jeff said get me involved early. A lot of times I get involved late in movement joint conversations. That's just not a good time. Contractors shouldn't be figuring out movement joint, control joint locations. It changes all the forces that go through your structural elements within your design. We have to know where they are before we can design anything. So I don't know how we could leave that up to contractors to locate them. Architects should always be locating them for veneers, and engineers have to locate them, an absolute must on their structural drawings. Otherwise, the design changes completely if we just allow it up to the contractor. It's going to be a very conservative design that's going to be the cover-all type of design if we just arbitrarily let control joints be wherever they want to be. So I think that's why MSJC said, no, the designers have to locate them. It's right within the code saying that you can't leave it up to the mason. The designers have to locate those. Again, we've touched on this stuff quite a bit. There's a guide, NCMA Tech Guide 10-2C, talks about movement joint locations, gives us a nice little diagram to use within the actual pages of the document. It talks about unreinforced masonry joints at openings. Veneers fall within this category. That's just fine. And this is the one that I'm talking about. When we get into reinforced lintels, reinforced jambs, we have plenty of reinforcement to prevent any cracks from occurring. Move that control joint away, and it can make a big difference in our lintel design. All right? So when we move the control joints away, what we're going to talk about next is arching action. The first couple slides that I showed you, how we've been doing this for quite a long time, or Mother Nature's been doing it quite a long time, spanning over these openings without any reinforcement. Arching action is really what's kind of the key principle to be able to span over the opening with no reinforcement in it. But we can't do that when we put a control joint at the edge of the opening. So if we see if any buildings I drive around and I see there's a control joint at the edge of the opening, it's just over designed. Right away, it's just a non-efficient design. It has to be, because we lose arching action. We lose the ability for the wall to just span over the opening all by itself, right? So we can't be putting those control joints at those locations any longer. All right, and then other things, shear walls. When I talk about how shear walls, you lose a lot of capacity when we move those joints to the openings. We have to allow those joints to be away so that we can use longer shear walls, which are going to be a lot more efficient designs, right? So moving joints away, we get an integrated lintel. The lintel is part of the overall wall system on each side of the opening. It actually participates in the lateral load resistance, the shear wall resistance, which is all a good thing. We just, again, there was a time where I think engineers maybe didn't really want to do this. I wouldn't have wanted to do this without the right software tools. That's a pretty complicated analysis, trying to figure out what the stiffness is and the load sharing between all these different elements, within the wall. That's not a simple thing to do. But once we get into finite element analysis and how that load is going to be distributed and shared down that wall through the lintel to the walls adjacent to it, it's not that hard of a task. It's not that difficult of a task. In fact, again, we do it all day, every day for concrete and steel. We just need to apply the same principles over here to masonry. So again, put that joint there, we lose arching action, we lose in-plane shear wall capacity. We don't want to do that. We want to gain all the capacity we have. Just pull that joint out and allow the reinforcement to prevent any cracks from occurring. Everybody's going to be happy. Engineers are going to be able to have a lot more efficient design. And I think, at the movement joint, we also talked about movement joint seminar that I did last year. We talked about moving control joints, maybe even beyond some of the industry standards when we add enough horizontal reinforcement. So a design like this, maybe where we have a lot of dock doors, we can go to, say, maybe 50 feet, 60 feet, 80 feet between control joints. And that's going to give me a much more integrated design between lintels and jambs. It's going to pull it all together, almost more like a moment frame, right? And that's stuff that we can do. Control joints don't have to be every 25 feet on center. Again, there's a lot of details there, but knowing where control joints have to be, where you can move them if you design for longer lengths of walls, will make our lintels much more efficient as well. Again, this slide that I always like to throw up here, again, just pull apart the wall a little bit, pull the face shell off. You can see there's no way a crack's going to occur here. I have reinforcement preventing that crack from mitigating from that corner any place up your wall, right? And so we don't need the control joint there. We just don't need it. Anybody that doesn't believe me, please stop by afterwards and let me talk to you just for a little bit about this. I think it's a very fundamental principle to efficient lintel design. So we want to make sure that we get this right. And then, again, this is a really big point. When I talk about, well, in the veneer, it can be in this location at the edge of the opening. In the backup walls, I'm talking about moving them away. And then you guys are thinking, well, then they're not going to align. And they don't need to align. In fact, there's some codes within the country that say they can't align. The veneer connectors that we have are flexible enough to be able to handle a little bit of a different movement within the walls, right? So we don't need to have those joints perfectly aligned, right? They can have different rules, different principles for them. All right, so loads on a lintel, what do I mean by that? I mean, again, I say that they're going to be different. It's going to be different depending on, control joint location, depending on material. So what exactly do I mean? We have different types of loads on a wall. We can have uniform loads on a wall, right? You have point loads that come from, say, beams and elements. And then we have this arching action thing that I keep referring to. What does that mean? You have the vertical loads, again, when they are placed on the wall, the red lines are kind of indicating to you the force that's going to be imparted upon the wall, right? And then the blue is really going to be the way that the wall is going to resist those forces. And you can kind of see those vertical elements, the vertical lines, going to be your column, your jam elements. And then what happens above the openings? You really have some diagonal compression struts that are being created in there. It's really what I would call arching action, right? And so arching action, all that is the loads that come down on the wall get distributed by the wall to the elements that go all the way down to the foundation, right? The lintel doesn't have to collect all of the load and then distribute it out to the edge of the openings. That's not the way we have to do a lintel design. It's really simple. I mean, just a simple 3-hinge arch will show us if I put a load in the center, right? And as long as I have H1 and V1 in the bottom left corner and bottom right corner are really going to be the vertical and horizontal reactions I need to resist that load on the arch, right? No matter how heavy the load is, I can resist it by not having any reinforcement in there, just by a compression arch, as long as I can achieve that H1 and V1, right? Stick with me for a second. Apologize going a little engineering on you guys. So if I just took a free body diagram, just kind of looked at one side of it, in fact, if the rise, the height of the arch, was half the length, right, I kind of have a 1-to-1 ratio. The load on the arch is going to be the same as the vertical load and the horizontal load presented there, right? And so within codes, there's kind of this empirical method of a 45-degree angle. And that really is kind of to simplify, what the vertical load would be and then the horizontal thrust load would be that I need to be able to do arching action. Well, that horizontal thrust load, if I go back here, that can't be achieved if I have a control joint there, right? It's just the wall's just going to slide off. It's going to slide over the control joint. I don't have any thrust capabilities when I have a wall with a control joint in it. Its purpose is to allow the wall to move. Well, now I'm losing that horizontal thrust force. Everything would just come crumbling down, right? So that's why that whole principle of getting control joints away is very, very important so that I can take the thrust load design-wise. All right, so the design loads just changed. If I look at the design loads for my lintels, this nice little diagram, which is in a document from NCMA, can you consider arching action? Look at the loads on the left, right? Much less than the loads on the right. If I can consider arching action, I really just have the self-weight to consider of the triangular area above that lintel, right? Flip back here just a second. That's a pretty small area. And this is an empirical method. This is actually a very conservative way to design a lintel, right? When I have arching action, empirical. Anytime you guys hear the words empirical, it should be conservative. I'm not talking about really kind of stretching and pushing the envelope. This is pretty basic stuff. So you can see it's a small area. That's the only load that I have to design for, plus concentrated loads. Concentrated loads are not what I would call joist loads on a roof. They're maybe girder reactions, very heavy forces that would come down on a masonry wall, right? So anytime I have concentrated loads, those would need to get imparted upon the lintel, but that's pretty rare. It's pretty rare to have a pretty heavy girder reaction on a wall that doesn't have a jamb or pilaster below it. So for the most part, most of the time, we just have those two loads to consider, the self-weight of the lintel itself and the little self-weight of the triangular area above the lintel. That's pretty small loads. Now, if I can't consider arching action, if I stick that control joint on the edge, look at the list on the right. Right? I have self-weight, I have that wall weight of the triangular area, but all the other area of the uniform loads put on the actual wall. The whole roof load has to get distributed through the lintel. And so all of a sudden, my loads get a lot heavier. So that's why I say when I put a control joint in different locations, we have to start to consider much higher loads for our design. And then not to forget about lateral loads. It's not going to be the focus of today, but certainly having a control joint away from the opening, my lateral force distribution occurs much more smoothly. It's going to be much more easily distributed to the elements around it when I can move away. All right, so I'm really left with, again, for the engineering side of this, do I have a simple analysis? If I have control joint there, I'm just left with a simple analysis for my design. It's going to be much higher forces. Do I have a simple analysis fixed end? That would be if I would have bottom reinforcement, top reinforcement lintels, just for you engineers out there. Or find an element analysis, which is really going to give me a pretty robust solution, right? I mean, it's pretty simple to look at those first two diagrams and say, yeah, I can do that by hand. I can do this pretty easily, right? Without finite element analysis there for engineers or masonry design for so long, that's what they were left with, those first two options. And they didn't really, it's not really a great opportunity to be efficient with your designs. It's when we get into the finite element analysis that we can really do some stuff. So traditional methods really look at simply supported end conditions, design moments only positive, shears greatest at the supports, need for shear steel primarily at the ends. Finite element methods really do incorporate the overall stiffness of the overall wall around it. A lot more words in here, but basically I can have this analysis be a lot more complex with finite element analysis. We have to encourage engineers to use finite element analysis. It's buildings like this. I can use an FEA and I can have an efficient masonry lintel. This is just a single-story building, very long spans, I need to put a piece of steel in there. We could have designed that very efficiently with masonry with some of the principles that we just talked about. This slide, I like to show this slide and talk about what goes on at these kind of complex structures as well, right? We have some deflected shapes. And what happens at the individual lintels, though? I can kind of look at it at a macro level, but then zoom in. I can see how the lintels interact with my jam elements. I can see all the forces, distribution of forces and movement of those elements. Finite element analysis just gives us more information, and we need to make sure that we're leveraging those tools to have an efficient design. So it's an important thing. And then this is just a project where, again, when somebody looks at this project, they might be thinking, well, I don't know if I can get that done. I can't do that design maybe in masonry. There's just so many openings. But again, if we can have continuous spans over these openings, if we can have these integrated jams and lintel elements connected to each other, it's actually not that bad. It's a pretty simple, straightforward, efficient design. And then just again, a quick color contour just to show you, how the force flows around these openings when we use the right tools. It's something that we can certainly leverage and utilize to have efficient designs. So the last little bit on this, and these are slides that, again, I spend a lot more time with engineering, but I just want to kind of show you some of the things that you can just visually see. It just kind of captures your eye to how these forces get distributed and flow around these openings with FEA. So if I just take a look at two walls, two openings, one long span, one kind of a short, typical maybe window layout, right? What am I looking at here? Kind of a 6-foot opening, 28-foot high wall. The height of the wall does make a difference, or a 14-foot wide opening. This is probably one that people are going to think, well, 14 feet, that's probably something I'm going to have to put a piece of steel in, right? I can't get a masonry lintel to work in that scenario. But we start to look at how the wall responds. How does the wall respond to those vertical loads on the wall? Well, just look at the axial forces. You can you see the arching action, right? The color contours are showing my axial stresses in the wall, right? The vertical pressure that I have, and you can see that area above the opening going down to red is going to be the lowest values, right? Right? And so then here I can numerically kind of give credence to that. Yeah, it does diminish as I get nearer to the actual opening itself. What happens when I have the larger span? Well, you'll notice here is what I have is a larger arch, right? This is probably a 60, 70 degree, right? Arch is not that 45-degree angle. So again, empirical design really does kind of constrain me to that 45 degree. But if I have a larger opening, all the finite element analysis program does is allows the wall to use the larger arches around the openings. Large openings don't mean that I have to put steel in. I just have to model them in. I can understand the behavior, understand what the forces and stresses are in the design. And again, numerically, we can see what the forces are very quickly within the wall design. Thrust forces, what do those look like? Those actually aren't that 1-to-1 ratio. That was an empirical method. That's something that you can very quickly do a quick empirical check to see if I have enough thrust capabilities. This wall scenario, I'm probably not too worried about. I have a long length of the wall outside of the opening to resist whatever the thrust loads are. But they're actually pretty small, right? I have so much height above the opening. You can see within the stress contours, you can see arch upon arch upon arch all the way up, the height of the wall. It very easily distributes the force. And these are like one kip. These are like a small value of thrust load. You can see them actually developing quite a bit up within the wall, right? It's not just right at the opening. Suddenly, boom, some thrust load gets shot out, from the lintel, right? It does get collected all the way up the wall. There's some arching going on throughout the wall panel. It just doesn't just happen just at the bottom, right? And even for the longer opening, granted, my thrust loads are a little bit higher. You can see the colors are a little bit more intense. I can see that I have more forces there. But again, looking at the values, you can see that they do start collecting up within the wall. It doesn't, again, wait till it gets to the opening and then shoot out some forces. In fact, it kind of balances a couple feet above the opening, and then it stops, giving it a thrust force, which I think is kind of interesting. When you have that extra height of wall, you have finite element analysis, you can see what the forces actually are. All right. I apologize. I'm just hammering you guys with numbers, but I think it's important to understand what the forces are and what's actually going on when I can use this tool, this advanced tool. Shear within the actual wall, you can see that it's pretty low. And I'm going to give some comparisons here in just a second. Or moments are just about nothing. Moments are just about nothing when I have a finite element analysis and that span over the opening, because there's so much arching going on, shallow, deep arches. It's really distributing that load out, and there's very little actual bending moment within the actual design. Even with the longer span openings, the moments are a fraction of what they would be versus if I would just have a simply supported element, right? So the other thing for the engineers in here, it does make a difference when I collect and look at these forces within finite element analysis. The depth of the member does make a difference. I'm not going to get into the weeds of why that is the case, but when you have a certain depth of member, say 24 inches, and I go to 48 inches, my load changes as well as my capacity. So that's something that's important to realize when we use finite element analysis, and it makes a lot of sense. We're grabbing more of the wall elements to collect the forces within them. So that's why we can see higher values here. Let me get to the actual comparison charts, which I think are pretty interesting. So here what I'm doing is I'm comparing the forces, the shear within my lintel, right there at the bottom highlighted in green, 2.3, 3.9, right? That's the shear that I would have to design for if it's a masonry lintel, control joints away. Pretty reasonable numbers. Well, what are they comparing against? The 6.1, the 14.2. That's the design loads that I have to use with the control joint at the opening with a steel lintel. So that's what I say, when you change out materials, you actually change the actual forces you need to design your lintel for. A lot of this has to do with arching action, right? So that's why it does make a difference. Just swapping between two different materials is not just, ham versus turkey. This is changing it fundamentally. This is an apple versus turkey. This is two different food groups. This is something that's completely different design-wise, right? So that was the shear. How about the moment? You can see the moment's even more of a stark contrast. The force is very low within the actual finite element analysis model, the moments that I have to design for, versus if I have a steel lintel, the 9.1, almost 50 foot kips of moment that I have to design for. And then if I went with a deeper lintel, which is probably more realistic, you can see the forces come up a little bit, but it's still, 20% of the force that I have to design for a masonry lintel versus a steel lintel because of the control joints, because of the limitations within a steel lintel, how it can grab the wall around it. That's a big difference. So not all lintels are created equal. Not all of them can do the same things. It makes a difference what material you use, what design options you use, because then you have to go back and iterate your design. If you go for masonry, you throw in a steel lintel, all of a sudden you're going to be jacking up your design forces pretty immensely. Hopefully, maybe with a lot of people doing steel lintel designs, I saw the hands. If I didn't see the hands, I knew that there was a few liars out there. Come on. Everybody has steel lintels and masonry walls at some point in time. And you have so much more force that you have to design for with those scenarios. All right, so different design options. With masonry, the main focus of the presentation, obviously, so we'll talk about that quite a bit. I'll talk about steel. It's common, but I generally don't think it needs to be. There's isolated times where a steel lintel may be required. We can talk about that a little bit, but to have it be the standard for lintels within masonry walls is really kind of a tragedy based on what I just showed you guys. We have so much higher forces that we have to accommodate, and then we have a lot of other architectural messes that you guys are having to clean up because we jam a piece of steel in there, right? It's a mess. I know none of you guys would like to have a steel lintel within an architectural element. It's just there's a lot of problems there. Precast is kind of the third solution that it's a nice in between. It's got some of the negatives of a steel lintel, but it's got some of the positive attributes of what I talked about masonry. It's a similar element. You guys probably aren't as concerned with it, except it just looks different. Maybe doesn't look as aesthetically pleasing, but who am I to judge? I'm an engineer. All right, so precast lintels, I mean, they fit within the masonry wall, right, if you have the right size. Precast lintels allow reinforcement to intersect with masonry. So what I mean by that is you can have precast elements that allow jam steel and lintel steel to cross one another to eliminate the need for a control joint right at the opening. So I think that's important. Probably going to have pinned end conditions for engineers. You guys know what that means. It's a higher design moment that we have to account for. Arching, again, is still available a lot of times for precast because we don't necessarily have to have a control joint, nor would I think it would be prudent a lot of times for precast elements within a masonry wall. So that's a big advantage. Similar material, so that means similar thermal movement. A lot of times steel lintels, the reason that the control joint's there, well, there's a lot of reasons, but one of them is you have to keep it when you have steel, regardless of everything else that I said today, because there's so much differential thermal movement between steel and masonry, especially within an exterior masonry wall. So you kind of have to keep the control joint there, and then you lose all of the beautiful, wonderful things that I just showed you guys, right? Those are beautiful and wonderful. Come on, you guys. Nice little finite element. Yeah.
So now when you're talking about precast, it's not just going to be a cube of concrete. You got to have some reinforcing sticking out of it and down in order for it
Yeah, so there's certain types of precast lintels, and I'll talk about those in kind of the next section. What precast works well, what doesn't would be more along the lines of a steel lintel. Yeah, some of it does end up being an element that's just kind of isolated, probably does want to have some joints around it. So that's a good question. Yeah, there's a certain type of precast that I'm talking about. Yeah. Yeah, so designed by precast supplier, that maybe is a positive, negative, having multiple designers, kind of like too many cooks in the kitchen, right? It's not necessarily a good thing. But the precast that I'm kind of an advocate for is the one that I'm showing up here, where you can see the top left image. You can see the jam steel is going to come up through that precast lintel. These precast lintels are a proprietary product, and you can see they also have a U shape. They have the reinforcement within them to span during construction, but you can add reinforcement for the overall design. So it's a nice kind of in between. It's not a masonry lintel. It's going to look, like a different material, but that's a pretty nice option. So you can get those joints away. You can take advantage of what the arching actions and stuff like that I was talking about. So steel lintels, again, very common. Should they be common? They're required to be concealed, which I know is a little bit of a pain. We have to put those soaps around them. We really have to think about, the dimensional sizes of the steel that we want to stick in there. Interrupts the masonry wall reinforcement, so that breaks apart, compartmentalizes my element. When I talk about breaking things apart, that's not necessarily a more robust and more efficient design, right? So interrupting wall reinforcement is not a good thing. Pinned end conditions, I haven't seen anybody come up with a good steel lintel that could have been a fixed end condition. You just typically put it in there. You don't have a lot of ties to the masonry because of that thermal movement thing that I was talking about. So you have pinned end conditions. You have a control joint that's typically in there because of that differential thermal movement. And so again, control joint being there, pinned end conditions, all of a sudden my design forces are 5 times higher than if I have a masonry or those precast lintels that I was showing you. So, the differential movement is probably not something that is as big of a deal, certainly if you go to an interior location. But if you go to an interior location, I think there's still even more reasons why you'd want to stick with masonry. Pretty easy to solve. And so, and I've, again, been doing this about 7 years. We've been talking to people, why do you use steel? If steel doesn't make sense, everybody agrees with me, it's got a lot of challenges. There's differential movement. You got to bury it, you got to conceal it, you got to use soaps, you got to cut the masonry around everything to fit. So why do we use it? The number one reason is to solve that shoring problem. I can just set the steel and I can keep going. Is kind of the thought. That's probably a 25-year-old idea, right? Maybe 30, maybe a little bit more than that. But 25, 30 years ago is probably really when it started to take hold. And when we were doing it then, it sounded like a good idea, but we maybe didn't understand all these different challenges that over the course of 25 years, we can see that it creates a lot of problems. It's something that you can use, but it's kind of difficult to do it right. We have reinforcement that we have to move. We have extra bars that we have to add. We have to put in some sort of anchoring for that lintel, but we need to allow some sort of sliding. So we have some slotted holes. We need to have some sort of a bearing pad that allows some sliding in there to create the control joint that's got to go horizontal for a little bit and then go vertical within that structural wall. All things that you can do, but I don't necessarily think that they're easy to do. So we want to make sure that if we have to use steel, which again I think is a 1% of the time where we have to use steel, we need to make sure that we're considering all the different elements about how to get this right. Because what happens if we don't get it right? We get this, right? If I said the number one place where I see cracks within masonry walls, it's steel lintels spanning over openings, and I see that crack, right? that differential movement, that steel moving differentially than the masonry. I don't have necessarily all those extra added little bars in there. I see, so I mean, it's a compromised bearing condition. Any engineers like this here, compromised bearing conditions? No? Come on. I mean, so it's a big deal, right? And so these are the challenges that we get faced with. We're solving one problem, and we've created a couple already, right? That we have to look at how are we going to solve this. Just creating the cavity wall scenario with a steel lintel. One, you have thermal bridging. We'll maybe get to that in a little bit if we have time. But the torsional loads on a steel lintel are not easy to resolve. If it's a wide flange, we have to add a lot of stiffeners. Then we have all the stiffeners that we have to cut all the soaps and all the different elements around, because wide flanges don't work well in torsion. So any types of loads like this, we have to start to account for. So there's problems, there's issues that we have to somehow work to resolve. And if, again, you get into that 1% scenario, I'd be really glad to help you solve, the different issues that you have with the steel lintel. Go ahead.
You got to talk about how you support the veneer at an opening when you're using, because
Yep, and towards the end. Yep. So again, we'll get there. We'll get there. So masonry lintels, again, it's integrated with the rest of the wall. It really creates a robust design between the lintel, the wall above the lintel, and the walls on each side. Fixed end conditions are available, top and bottom reinforcement in the lintel. Pinned end conditions, you can certainly do that. Arching action is easily achieved. We should never, never, never do a masonry lintel with a control joint at the end of the opening. Hopefully I've covered that, hammered that. I've said it 20 times. What's the counter, up to 21 now, Jeff? All right, so masonry lintels do have the inherent ability to arch over the opening. If you have an arched doorway, you in fact don't need any reinforcement, no steel within that opening, right? You saw the early pictures. We can do this. We can do that for a long time in a concrete or a stone type of material. Built in place or prefabricated. Again, prefabrication is something that we're certainly moving to as an industry. We're learning about what we can prefabricate, what we can do maybe in a shop, shipped to the site, what we can do on site, on the ground, maybe in a certain location, and then just lift them into place and set them into place. So there's different types of prefabrication that I see. So longer spans being available. We don't have to do some elaborate shoring to build long span masonry lintels. 4 feet to 12 feet is pretty common. We just did a design for up to 52 feet long masonry lintels, 12 courses deep. It was a pretty sizable wall, pretty sizable opening, but you can certainly do a lot of stuff with masonry. There's no inherent limitations to the span as long as you have the depth, right? Just like anything else. But again, showed this picture before, show it again. I mean, it's going to be integrated with the jambs around it. Just show a project that we helped with. Again, you have the lintel that spans over the opening that's crossing with those jamb reinforcement. One of the things that the contractors wanted me to talk about is the fact that you have grout in a lot of these locations. This is a top wall. There's a bearing wall, a two-story school. There's a lot of times where adding a little bit of extra depth is something that they're just going to do anyway. They don't want to start and stop grout multiple times. So sometimes when I'm talking about, I don't need 4 courses, I don't need 5 or 6 courses, sometimes you're going to get it anyway just because of the ease of construction to grout everything solid above an opening, especially in a multiple story scenario. So when I talk about doing 1 or 2 course lintels, I don't mean make sure it's 2 courses, make sure you jam in stirrups in there because we want to make sure it's just a 2-course lintel. Sam said I could do it, so I'm going to do it, and you don't have to do it. A lot of times if it's these type of designs, think about how it's going to be constructed. Think about the depth that you're probably going to get regardless. So what are my different reinforcement options? Certainly bottom, start with the middle. Bottom is going to be common. It's always been done. Everybody's always did bottom reinforcement. Top reinforcement, there's some heartburn within the engineering community about top reinforcement. I learned that when I was at Bentley. We came out with this finite element analysis tool that had fixity from the lintel to the wall elements around it. I think in the last 7 or 8 years since that first came out, engineers are warming up to the idea. People have said to me, well, I've never put top reinforcement in there and I don't have any lintels failing. Well, yeah, because it cracks. Engineers know that, right? It's going to crack, because you have that negative moment there. You don't have the reinforcement to resist the moment, so you have some little cracks that created. If you want a really robust design, you add, the same amount of reinforcement, but just split it between top and bottom, right? And top reinforcement should be becoming more and more common in masonry design, masonry lintel design. Lastly, down there, stirrups. Stirrups are an option. Sometimes people will be like, I can't put a stirrup within a masonry wall. Well, it depends, right? We need to be careful about how much and what thickness of wall we're talking about, but stirrups can be used in some of those limited depth scenarios if we have pretty heavy loads designing for. So pretty typical layout reinforcement here. And then the stirrups, I guess the point that I would make is if you get into an 8-inch wall, 6-inch wall, you could use stirrups, but just a single leg stirrup, right? Let's be practical, just kind of similar to the one vertical bar that you would typically put within a wall, you can get away with as a stirrup. You don't want to put double leg stirrups in a 6-inch or an 8-inch wall, right? Thicker walls, you can certainly do that 10, 12, 16 inches thick. We certainly have more options for stirrups. But before we do that, I mean, certainly adding the additional depth makes more sense. All right, so I think, we talked about torsional capacity, lintels with that eccentric load. Steel really doesn't work well at all. Masonry is going to work very well. It's going to be very efficient. It's interconnected. I keep saying that, right? It's connected with the wall above it. Having some eccentrically loaded lintel, like the one that I show on the screen, one, it's a nice thermal break, right? Which, again, architects are seeing that, and that's a great thing. We're doing it at shelf angles, but do it at lintels as well. Create that thermal break. Maybe you have minimal thermal transfer with that design, and we're putting some torsional load on the wall, but the wall is going to take it out in bending. It's not just a lintel that's going to have to resist it in torsion. It's more efficient. It's a better design. When I talk about prefabrication, here's a job that I just visited last week. This design did have some stirrups in it, but they didn't have to prefabricate the whole depth. You can see that they're basically prefabricating half the depth. That's all you need to prefabricate. You don't have to go the 4-6 courses and prefabricate everything and lift this very heavy, awkward piece into place. 1 or 2 course lintels prefabricating works pretty well. All right, so again, what do we talk about today? We talked about using the right strength. We got to use the right strength of masonry. Architects, check your engineers. Engineers, please check your typical standards and details. Make sure that we're using the right strength. Control joints away from openings allows arching action. It makes it just better, whether it's a precast design or a masonry design. We have a lot of design efficiencies. It's a much more robust solution when we can use arching action. Consider FEA. FEA is going to capture that arching action, right? You can see it from the slide. You can see the arches occurring within the stress contours. Deep beams are certainly an option. We didn't have a chance to talk about that, but you can use the full depth. When you talk about lintels over openings, I can use the full 20 feet of depth to design as a lintel. It doesn't have to be grouted solid. We have a lot of options that we can look at when I'm spanning over openings. And then just a couple suggestions there. If we want to increase the moment capacity, we just add top and bottom reinforcement. Add shear capacity, just add more depth, or you add stirrups. We have a lot of ways to resolve different forces within designs. I think I got about 10 minutes left here. All right, so some of the detail considerations, some of the additional architectural considerations to think about. For precast, you certainly have to be able to lift those into place. A lot of times for precast lintels, if they're not the U-shaped members, then they do get pretty heavy and pretty difficult to deal with. Considering modular coursing, right? 8 inches, 16 inches, 24 inches. We've seen projects that look like this, right? 12-inch deep. That's not any good. It looks kind of silly. Not necessarily a good architectural finish. Special anchoring, you want to make sure that as you set this, as it gets deeper, even more anchoring that you have to consider to make sure that you don't have any roll-off in the design. So there's some things that we have to think about. You have coordination. You have to order the precast element. Masonry, we talked about this in a lot of seminars. Scheduling-wise, masonry is typically on some pallet someplace ready to get built the next day. Yes, there's steps in there, but it's ready to use right away. So scheduling-wise, precast, we have to think about that just a little bit more. A lot of times what I like to see people do is give contractors options. Say if they want to use precast, here's the design loads that you have to have your precaster design them for so you can use them, or here's a masonry option, which is what the coalition would be glad to help you guys with. So you have some coordination issues. You have, again, that scheduling issue. This is a project that I actually did the design for the engineer on, where we did allow those precast lintels, which worked really good. And it was a contractor-led initiative. Again, we gave the contractor some options. They thought this would work pretty good with their scheduling. They could get them. They were available and put them in place. Steel, again, should they be common? Again, they're also a scheduling issue. You certainly have to have them prefabricated. You have some lead time there. You have to have some bottom plate fabrication. You have to have corrosion protection. You know, the last thing that we want to see is rust bleeding on a wall, interior, exterior. When we have steel, we have to think about corrosion protection. Bearing plates often required. Unfortunately, bearing plates can be those big, nasty, ugly things that go at the end of your steel lintels, make those coursing, the mortar joints look kind of silly. So we have some issues that we have to deal with there. And then thermal bridging. We don't really have an ability to have that separated thermal break or minimize the thermal bridging. With steel lintels, we kind of have that straight thermal transfer outside to inside. And again, it was used to solve one problem, right? We created 5 or 6 engineering problems. We created, you can see the several different items that you have to address here. You know, how do you detail it? Certainly you have wide flange. You could use HSS, double angles, but all of them have some of those same inherent issues. You know, probably the biggest one is making sure that you use the right depth. Just because you use a W16 steel member doesn't mean that it's going to fit within coursing. There's still a lot of cutting that has to occur within those soaps and blocks as you fit it into place. So you've solved one shoring problem, but it's not necessarily schedule friendly. We have to still add those soaps so people don't see that steel lintel. Nobody wants to see the steel. So I solved one, but I maybe created a lot of problems just because that depth of member doesn't fall right in line with the mortar joints, right? And just a quick picture to illustrate that. You know, we have to think about that as we're building these things up. And just all the different rust problems that compromise bearing condition, where the reinforcement goes. We have a lot of issues that get created, which then goes back to this compromised bearing condition again. Again, what do we do with those bearing plates? When we have to have that steel lintel, you know, those bearing plates are kind of an issue. If they're exposed, then I think you have that potential for rusting and bleeding to happen. Especially sometimes they get thicker than the actual mortar joint. That even looks worse. So we have to get comfortable and familiar with how to design bearing plates. You, in fact, never should see a bearing plate. So as you maybe have to do a steel lintel, still the bearing plates never should come to the edge of the wall. So that's a little tip for a different day. You know, you should never see those in your designs. Even though I'm not an advocate for steel lintels, if you do put them in there, make sure you don't see those bearing plates. We can certainly reduce them in width on every design and still have the same design capacity. Little nugget for you to think about. So complicated to do right. Masonry lintels, again, fast, economical, moves at the same rate of the wall. What I'd like to show is just really kind of quickly here, there's a lot of different ways. You don't have to prefabricate. There's a lot of different ways to solve the shoring problem. A couple angles that they slide out later. This was actually a long span, a 26-foot long, where they got pretty elaborate with what is a temporary shoring for a masonry lintel. They didn't want to leave the steel in place because of all the other problems that it creates. Use a wide flange member just for shoring, and then they're going to pull that out later. Or a couple 2x4s. But like I said, prefabrication I think is something, this is a few years old, this project. You pick it up, lift it into place. Project that I just looked at last week, you could see him prefabricating it in the shop, prefabricating some on site. You can see the ends of the lintels left out for the jam reinforcement to come up through. And then you can see it actually set in place within the masonry wall. Now the project up in Madison, a multiple span prefabricated lintel. Certainly that's a good design option as well. So I think we're running just right at time. You know, I think there's a lot of different things that you can do with masonry lintels. Let me see, jump down here. There's a lot of other prefabrications we can look at. You know, brick lintels that could be prefabricated. And a project from a few years ago that we could have looked at there. But, you know, masonry lintels are, again, that lintel that can be integrated, robust, part of the wall design, helps us with our overall lintel design when we choose masonry, but it helps us in terms of our shear wall design or out-of-plane bending. There's so many better ways to design my wall once I use masonry lintels. We can use some of those other options, but just recognize all the complications that we add to when I add a precast lintel or when I add steel lintels. We maybe sometimes have to choose those options, but let's make sure we do it wisely. We don't want to have compromised bearing conditions. We don't want to have rust bleeding on wall. Use the right tools. Finite element analysis tools down there at the bottom are programs that engineers use all day, every day, that have inherent masonry materials, masonry design options for the wall elements, for lintels, stuff that people should be using. So with that, we'll go ahead and take any questions that you guys have. I mean, it's a lot of information, but again, this is a 4-hour seminar that we compressed down into one. I had a hard time doing it. If you guys have, any thoughts or projects that you guys might want to have us look at for, what would this look like, Sam, for a masonry lintel? Please go ahead and send that to Jeff, and Jeff and I can work together in solving those designs.
Questions? Couple things. Certificates are downstairs when you're walking out. My card's there as well. Should be there.
You can hear me. My card is there as well. Certificates. Anybody doing design work in the city? Okay. I've heard this from a couple sources recently. The city of Chicago is no longer allowing shaft walls for elevator shafts, stair towers. It's requiring CMU.
No drywall for sure.
No drywall. No drywall. Anybody else hear that? No? You did? Okay. Okay. All right. Again, there's some brochures downstairs for some of these upcoming seminars. The online webinar on Friday, October 13th for that Revit plugin for masonry. I have some copies here if you want it as a link.